Good evening and welcome to tonight's lecture on the Rolls-Royce Ultra Demonstration Programme. Tonight's lecture is on the Rolls-Royce Ultra Demonstration Programme. We have Andy Geer with us tonight, who leads both the technical programme management aspects of this programme for Rolls-Royce. It's the next generation of Rolls-Royce civil gas turbine engines. And it'll be interesting to hear how that program will develop, obviously in light of the COVID-19 impacts, the environmental challenges that are on air travel now, hopefully how it will lead to lower fuel burn, reduced emissions, use of sustainability fuels, etc. So I'm now going to hand over to Andy, who will take us through the presentation.
Great, Paul. Thank you very much for the introduction, and welcome, ladies and gentlemen. Hope I can give you an entertaining summary of where the UltraFan technology programme is as we move through 2021. Paul touched on a few of the areas I'm going to cover in the presentation. Actually, I'll set a little bit of context. We're executing here a very exciting and complicated technology introduction programme for the next generation of class-leading gas turbines. But before I get into that, I just want to share some of the context against which we're trying to deliver this piece of work. I'll talk then about the progress and structure of the programme and some of the future challenges that we face, perhaps particularly as we enter a very challenging phase of the programme, that is to build our first test vehicle and start collecting data from it. Inevitably, I suppose, given the timing, I have to show a picture of a horrible virus to start the context. Certainly when I picked up this programme, leading both the technical and programme side of it, I had no expectation, no idea that we would face the challenges we do associated with COVID at the moment. As you will well imagine, the impact on the aerospace aviation sector has been enormous. The IATA data there shows you the extent of reduction in service operations, civil operations, absolutely massive. And of course, that affects Rolls-Royce and all of the industry to a huge degree, both in terms of reducing the available revenue and therefore the affordability for technology injection, but also perhaps for changing people's perspective on what aviation has been, is right now and could be into the future. Perhaps the thing that's hardest for us to deal with at the moment is the expectation that a return to the kind of traffic levels we were used to in 2019 may take as long as 2024. And therefore we have to think about bridging this period of time in the most effective way we can. And for a technologist like me, that's quite challenging. So tough timing to try and bring a new generation of technology to market. What's inspiring the investment in UltraFan is really summarised by these industry targets on emissions. And perhaps these targets were here even before the impact of COVID-19, of course, and a lot of attention on emissions and noise. And with emissions comes both fuel burn reduction and an improvement in the quality of the emissions produced by an engine for a given fuel burn. But I think it's fair to say one of the impacts of COVID-19 has been a bit of a step change in the world in what they expect of the aviation industry as it re-emerges from the downturn. So more than ever, the emphasis has become one on moving towards a net zero carbon position. And you can see on the right-hand side of this chart, UK aviation target has been set to achieve net zero carbon by 2050. Rolls-Royce has joined that charge, that challenge, and of course in our case it is a technology-led achievement, or needs to be a technology-led achievement to get to net zero carbon. Really challenging objective, and I'm pleased to say what I'm going to spend most of my time this evening talking about, the UltraFan, is a significant step in that direction. Before I go there though, we should be aware of the fact that within aviation there are almost, there's a huge number of technologies competing to be the technology of choice as we move to that more sustainable, decarbonised future. And this chart tries to summarize that in a very pictorial form. So showing really, air transportation all the way from urban air mobility, air taxis, if you like, through to the more classic wide body and large bizjet aeroplanes, all kinds of technology that smart people are trying to apply to the range of aviation operation. On the smaller end of the market, all electric configurations or hydrogen fuel cell configurations. On the larger and most particularly long range end of the market, classic gas turbines, but potentially modified in some way, either with an electric configuration to support them, or at the very least, combusting sustainable aviation fuel. That is, fuels that are produced in a net zero carbon, closed carbon cycle way. It's a brave vision, and of course it's challenging to see a situation where we have to develop potentially multiple technologies to deal with fragmentation of the way aviation is constructed, from short range, small aircraft to long range, large aircraft. Rolls-Royce, of course, as a supplier of power and particularly in aviation propulsion, wants to be engaged in all these areas. And as a leader in technology, we're striving to bring technologies to market that can address as much of this sector as possible. This is a bit of a rogues gallery, isn't it? But here you see some chief technology officers from 7 of the largest companies operative in the aerospace business: Airbus, Boeing, Dassault, GE, Rolls-Royce, Safran and UTC. 7 CTOs who probably wouldn't normally sit next to each other without a bit of food fight going on, but coming together here because the industry needs to change, and they're recognizing the industry needs to change at a very high level. No one company, no one part of the industry can achieve decarbonisation or sustainable flight. We have to cooperate in some ways at aircraft level, at engine level, and indeed in provision of fuel and fuel logistics. So really interesting times that we're living in, where you see these competing companies, usually competing companies, coming together to collaborate and move the industry to a new place. Now I'm a Rolls-Royce guy, so I'll offer a Rolls-Royce view maybe. Here's a cartoon, and it is only a cartoon, but something that shows the kind of very different world we may find ourselves living in the not too distant future. The diagram here is self-explanatory, but it basically shows you a situation where you could use hydrogen or synthetically derived fuel coming from a zero carbon electricity power generation system, either to drive and power aircraft directly in terms of combusting hydrogen, or to provide a feedstock for synthesis of synthetic kerosene to support those aircraft or other vehicle operations in a net zero carbon way. Now, if you think about it, I'm here talking about gas turbines. That's one small part of this whole diagram. So what's represented on this page is a massive change in industry, in society, and in the way future aviation sector and future industrial sector would have to cooperate in order to make this kind of clean, versatile power truly available. So now let's come to what Rolls-Royce is doing. Rolls-Royce is operative in 3 pillars. We describe them as 3 pillars of investment and technology development, represented on this chart. I'm going to concentrate mostly on what to me is a very pretty picture on the left, artist impression of an UltraFan, so a next generation class leading gas turbine. But we can't ignore the fact that also on the other side of the diagram there are radical alternatives of electrification, hydrogen combustion and drop-in sustainable fuels that may replace gas turbines or enhance the operation of a gas turbine in certain sectors, as I've indicated. So in reality, all of these areas have a part to play, and as a technology company, Rolls-Royce therefore has to develop capability in all these areas. Perhaps equally important, our job actually very often is to integrate other people's technology with our own to get from a propulsion system or an element of a propulsion system to a fully integrated platform solution. So 3 key areas of focus: evolving the gas turbine, developing radical alternatives, and integrating to platform level, all at the same time as motivating the wider industry to develop availability of zero carbon or net zero carbon fuel stocks. So a quick aside, electrification. In Rolls-Royce's history, Rolls-Royce started out as an electrical motor machine, but it's a long time since we were engaged in that business. Nonetheless, we recognise electrification in aerospace is going to change major parts of society, major parts of industry. We're seeing that happen now. Lots of new startup companies active in electrical propulsion, active in air mobility in particular, flying taxi. But also active in providing parts of propulsion systems, parts of electrical control systems. And as I mentioned already, you can see in society, if we're going to move to a very much more electrical set of solutions, there's going to be a whole level of infrastructure investment required to achieve that. I've no doubt you'll talk amongst yourselves about that in the automotive space. It's equally true and probably a level of challenge higher in aviation space. Rolls-Royce activity is both incremental, evolutionary technologies, and revolutionary technologies, looking more at disruptive approach to the marketplace. And the images here perhaps show you some of the extremes of that. So as electrification becomes more common in civil aerospace, you could imagine a situation where we evolve a gas turbine to have embedded electrical power generation, which is what you see in the top image, or much more revolutionary electric or hybrid electric systems. In this case, the picture shows gas turbines producing raw electrical power, which is then distributed to multiple propulsors. So electrical propulsion, but still backed up with a gas turbine. There are many pictures and many ideas, so it's a very fast changing area. However, when you look at it from our perspective, underpinned by investment in technology, both in electrical machines and the gas turbines that might produce the raw power. A little bit different now, something you're going to see in the press before long. As interested aviation watchers, you may already be well aware, Rolls-Royce is doing some work on a project called Axel, pictured here. So a small, all-electric, single-seat aircraft designed to push the airspeed record, push the airspeed of all electrical flight, I should say. Really exciting project for the company to work on. Now, it's a bit of a headline grabber, but why is Rolls-Royce doing this? Why is it spending money in tough times on a racing machine? Well, the answer is learning by doing. The answer is there's no better way to find out how to deliver electric propulsion than trying it. And that's what's happening through this process. So in actual fact, if I skip to the next picture, there you can see a photograph of the aeroplane outside the hangar, just about to undergo some ground runs just a few days ago. So electric propulsion in one form or another is coming. Quite what market develops behind it, we don't know. Rolls-Royce is absolutely engaged in the technology journey to be a part of that new market. Just one picture at the other end of the market sector. So that racing machine is about a 400 kilowatt animal. This is a 2.5 megawatt animal. So something that might look like a hybrid electric system, gas turbine close coupled to a megawatt class electric generator for something that could support that kind of revolutionary distributed power aviation solution. You can see the tagline for Rolls-Royce, Pioneers of Power. This is a really interesting example of my 3 pillars picture. A highly efficient gas turbine, closely connected to a highly efficient electrical machine for use in a hybrid system. The eagle-eyed will have spotted in my context chart, talk about hydrogen. A lot of discussion ongoing about hydrogen as a means to produce zero carbon aviation. And I've just summarised here a few of the issues or a few of the factors that would attract you to using hydrogen as a fuel, perhaps. It's clean, it only produces water as an emissions product. You can derive it from a number of different sources, and of course it's an effective and fairly power dense fuel supply. So on the face of it, lots of interest in hydrogen as an alternate power supply. But in aviation, there's some real challenges here. Burning the fuel is probably relatively low down the list of challenges compared to some of the other things that we need to understand and deal with if we're going to move into this kind of space. So 4 aspects of flying hydrogen which need to be grappled with. A lot of discussion about contrails and whether contrails contribute significantly to environmental damage or not. So hydrogen is a clean fuel, but it produces more water vapour. So water vapour at altitude would mean contrails, and we need to understand what that means. Plus, of course, as you can see from the other pictures, there are some quite considerable logistic challenges associated with the use of hydrogen as an aviation fuel. Power density to volume, storage requirements, temperature requirements. So I really put that on the table to show that there are other challenges around us right now to deal with. How might those come together? And if I emphasize again, Rolls-Royce's ability to integrate, here's a situation where we might see hydrogen being integrated with world-class gas turbine technology to produce one of a number of aviation architectures. Fuel cell to power, direct, no gas turbine involved, or more likely, hybrid systems where a gas turbine combusts hydrogen or acts in a boost mode, combusting hydrogen alongside fuel cell technology. Now that's quite a bit of context behind why Rolls-Royce is working on 3 pillars of technology investment: electrification, hydrogen power, gas turbines. I'm a gas turbine guy, right? My job is to deliver a gas turbine. And I'm pleased to say, in a narrow context, a great many of the solutions I've just shown you in context still rely fundamentally on a gas turbine producing raw power, even if that power is consumed in a slightly different way, into a hybrid cycle or a more electric cycle. So the challenge ahead of me and my team is very clear. It's to produce an UltraFan, a vision and a technically integrated solution of the next generation of gas turbines. What they burn, how they burn it, and how they provide the power, we can be flexible on that, but you fundamentally need a good, capable gas turbine to start the race. So without more ado, let me talk about what the UltraFan is as that next generation gas turbine. Here's an artist's impression, or a general arrangement, if you like, a picture of an UltraFan. And badged on it are some of the technologies that have to come together in order to make an UltraFan engine work and to be super efficient. You can read the words for yourselves, but I'll highlight some of them. Those in green boxes, that is a low-speed carbon titanium fan system, power gearbox, an advanced 3 or revised work split core, and a high-speed multi-stage IP turbine system. Those 4 pieces of technology become absolutely essential to produce an UltraFan. Take away any one of those and you don't have an UltraFan machine. So those 4 pieces of technology are the prime delivery from the UltraFan Demonstrator program, making sure we can bring all those things together, integrate them, and have a super efficient engine as a result. Things in grey then are either enabling technologies, so they're things we would like to do alongside those essentials, or they're things that bring a better attribute to the engine. So for example, if I could focus there on hybrid ceramic bearings, that's a modern technology bearing using ceramic rolling elements that allows us to have a smaller bearing for a given load configuration than a traditional metallic bearing. It's not essential for an UltraFan, but it's highly desirable because it allows us to improve the engine's attributes. So there we are, that there is technology pretty much front to back in the UltraFan engine, some essential, some beneficial. And my job and the job of my team is to bring all of these technologies to realization and to integrate them into a single engine solution that we can push through trial and development and learn from it. I'll show you some pictures later on that these component parts for all of these technologies are now coming together. We've started the build of the engine and we intend to test it next year. A quick step back. If you're familiar with jet engines and aviation, I'm probably teaching grandma to suck eggs here, but why are we driving an UltraFan and why does it look the shape it does? Fundamentally, it comes down to what produces the most efficient power in a civil aviation, civil aerospace context. And that's two things shown here in orange and blue. So in orange, the first thing you need in a highly efficient engine is a very efficient and power dense core, a gas generator. So the part of the engine that receives the fuel, pressurizes the air and produces power available to drive the fan system. So a very thermally efficient, power dense core becomes an essential for UltraFan, and a lot of the technologies we're working on drive that. Smaller core, higher overall pressure ratio, more efficient. That gets matched then to the section in blue, a larger fan for an overall increase in bypass ratio, a larger fan running slower in order to move a higher mass of air at lower speed, which gives you a propulsive efficiency advantage. So as technology allows it, and you'll know this from the historical trends in the business, as technology allows it, engines have moved to higher overall pressure ratios in the core, driving bigger bypass ratios, slower fans, bigger fans, as being the most efficient way to produce civil thrust. In the case of the UltraFan, the fan becomes so large and the bypass ratio so high that having a turbine running at the same speed as the fan would be detrimental. That turbine would become very big and is running too slowly, really, to be effective as a turbine machine. So we gain advantage in the UltraFan by putting a power gearbox between the turbine, multi-stage turbine at the back, and the fan system at the front. In the case of the UltraFan, that power gearbox is running at about a 4:1 gear ratio, so the fan is turning 4 times as slowly as the IP turbine at the back of the machine. That allows you to have both a super efficient fan and a super efficient high-speed IP turbine. So it's that fundamental physics, if you like, which is driving the overall configuration of UltraFan and leads to the inclusion of the technologies that I showed you on the previous slide. A low-speed carbon titanium fan system, a power gearbox, a power-dense, energy-efficient core, and a high-speed multi-stage turbine to drive the fan. Now, when we put this program of work together for the UltraFan, which was quite a while ago now within Rolls-Royce, it was kicked off in 2013, 2014. We laid out a program of work which is represented by this cartoon. The upper part of the diagram on the right schematically shows you the shape of the program. So if you're eagle-eyed, you'll notice there that we have the essential technologies: power gearbox, fan, high-speed IP turbine, and what I've called here whole engine. Those four essential technologies coming together and iterating over time as we move through an engine development program that comprises 3 ground test vehicles and a single flight test vehicle. So that program of work provides a means for us to bring together, explore, improve and productionize, or come close to productionizing, the technologies that are necessary for an UltraFan to be successful, culminating ultimately in flying testbed experimental flight test operation to prove that the engine operates successfully at altitude. The lower half of the diagram is slightly different. It shows you here a risk waterfall. So the vertical axis here is technologically driven risk. So when we bring together all the new technologies that feature in UltraFan, inevitably we're representing quite a lot of engineering risk there, the power of discovery. And measured over time, the purpose of the UltraFan Demonstrator program then is to drive out those technological risks by building system, subsystem and product system design, by pushing those subsystem components through test, and ultimately building engines, testing engines, in order to fully understand how these technologies behave and how we should optimize them for a future product. So we built the UltraFan Demonstrator program around that technology risk mitigation idea, and constructed a program that would drive risk out progressively as we move through this 4-engined EDP. Now, the title of the lecture is the UltraFan Demonstrator. That is because this program does not go to a product. It is a technology demonstration activity that finishes with the experimental flight test of an engine. Beyond that, you then need to move into a certification and productionization aspect for whatever UltraFan that the civil aerospace market needs and desires. So where are we today? The essential technologies, the 4 essentials for the UltraFan program, I'm pleased to say, have met the necessary standard for our first demonstration engine to run in the EDP, or Engine Development Program. That's rather unimaginatively titled UF001, UltraFan number 1. And I've summarised here the work that's gone in already. Before we get to this place in 2021, Advanced 3 was a precursor engine, actually built around an XWB and a Trent 1000 component set with a new core, new power dense core inserted in the middle. That Advanced 3 UltraFan core technology completed 130 hours running, mapping out the basic performance and thermal capability of all of the hot section, the power dense core for UltraFan. Very successful program. You can see a photograph there of the engine installed in the test cell. Collected a ton of data from that engine. It has about 3,000 lines of instrumentation in it. And we captured, I think it's approaching 3 terabytes of data from that engine, which we need to analyse and understand to make sure we can optimise those technologies into the UltraFan and into a future product. Fundamentally, though, it comes down to some very simple summaries. That engine proved the basic cycle capability of the core, and it met the thermal efficiency expectation. In other words, the fuel burn performance. We've taken that engine partially to pieces to inspect its condition, and it's actually in rebuild right now. Once it's completed rebuild, it will go on and do further test work, again supporting its big brother, the UltraFan, which gains the LP system to go with this advanced technology core. Equally important, the second essential technology, and in some respects perhaps the star of the show, the power gearbox. So we've run a couple of different standards of power gearbox so far, and I'm pleased to show this photograph here shows you what we call a DP2 standard, so our second major iteration of gearbox standard on test in Germany, in a specially built test rig that's enabled to test this kind of gearbox. That unit produced max takeoff power, that is target torque and speed, at its target efficiency levels. That's a massive achievement for us and a big piece of technology de-risking. If I put that into context, I'm hoping a little pop-up will appear. There we are. If I put that into context, here are some of the statistics that go with that power gearbox. DP20501 is the actual test unit, shown here in the rig. Max takeoff torque, 82 kilonewton meters. Max takeoff speed, 6,000 RPM. 52 megawatts of transformed power. And it does all that in about a 1 cubic meter space of gearbox. So I put it in other words, that's 500 family saloon car power transmissions squeezed into a 1 cubic meter space. An incredible thing to see, and I think a measure of the power density that you have to deal with if you're going to make an engine of this efficiency level to this kind of power capability. Third essential technology, composite titanium fan system. Picture here actually of a slightly subscale unit on test. This is undergoing or about to undergo what we call a trailing blade impact test. So that's where we explosively release a blade and look at how the engine system controls that release. That's a look ahead to a certification requirement that all such fan blades have to meet. Huge amount of work been done on the UltraFan to bring that composite fan system to readiness, and I'm pleased to say we now have a design that meets all of the aerodynamic impact, load and stability criteria that it needs to support the sea level operation of the UltraFan. That's an investment of about 10 years of effort to get to that place on a composite blade, so a major undertaking in its own right before the UltraFan program really gets started. And then the fourth and final piece of technology, high-speed intermediate pressure turbines. So if you remember the previous picture, this is the machine at the back of the UltraFan that drives both the IP compressor, front of the core, but also the fan system. So it's driving that fan system through a gearbox. Picture here shows you an aerodynamic rig test facility in ITP in Spain, who are the design make providers for our high-speed IP turbine, and a really successful aerodynamic rig test program completed on that high-speed IP turbine. So there we have in summary the four essential technologies, all having met their precursor test requirements to say they're ready to go into a sea level engine. If I just sit back slightly to the power gearbox, and I've emphasised its power density, this chart really just tries to summarise the volume of work that's involved in an engineering programme of this nature. So it's a validation pyramid, you can see why from the shape, but basically here at the bottom of the diagram we have a very broad and extensive range of analysis techniques in cyberspace, if you like, and then above that subscale component and subsystem and subsystem level rig testing, all of which takes place before we move to an engine level test. So we've been marching over time through this pyramid of validation, building a sound base analytically, then producing component level test data to validate those models, and then finally pulling together parts of the whole system in order to test those individual parts, all of it leaning towards and looking towards integration of the product into a full engine test. Shown this pyramid for the power gearbox, there are equivalent pyramids for all of the major technologies within the UltraFan. So composite titanium fan system, the high-speed turbine, the core, even some of the component technologies. It really just emphasises how much work is involved in bringing a new generation engine to the point of readiness. How do I know it's nearly ready? Well, here are the parts. So these are photographs of just some of the complex parts that are now arriving in Derby, ready to be built into the first UltraFan engine. Huge composite fan case, 4 of the 18 composite fan blades, front engine structure, center engine structure, triple stage blisk from the HP compressor, and some jazzy additive layer manufactured cooling devices that fit towards the back end of the engine. 6 pictures just showing you the complex nature of the engines that we're manufacturing. These parts have come, some of them from the UK, I'm happy to say, others from elsewhere in the world, and some of them through pretty novel manufacturing techniques, whether that's the automatic tape laying involved in blade and case, or additive layer deposition involved in these cooling devices. I included those pictures because it's worth remembering whilst we're developing technology for a jet engine here in the shape of the UltraFan, we are of course also developing novel supply chains and manufacturing processes on the way, if you like, because they're necessary to produce component parts to the standard we wish. A further view, these are shots taken within the assembly facility within Derby quite recently. And they show us actually using a couple of things here which emphasize that not only are we producing an engine design and learning new processes in manufacture, we're actually learning new processes in assembly and assembly control too. And that's a secondary objective of the demonstrator program for UltraFan. So the left picture here shows a kit of parts. It's actually part of the complex vane mechanism for the HP compressor and the electronic instruction process, which is used to control build of those parts. In the centre, this gentleman here, you can see, stood alongside 3D printed component parts. It looks like those rocket lollies you used to be able to get from the sweet shop, but this is a big set of components here, and we're printing these components out so that we can work with the tooling, which is all new for this engine as well, to make sure that the component parts will fit to that assembly tooling and that we understand how to manipulate such large components safely. Engine 1, UltraFan 1, is being built in a facility we're calling Demo Works in Derby. So we've actually taken one of our older facilities in Derby that used to be used for experimental build and reconfigured it to be concentrated around UltraFan build. Component parts will enter that facility and the full engine will leave. So all elements of that engine build will be done in the same place by a small team that is working hard to familiarise itself with what is quite a different engine configuration for us. The core engine module build packs are in progressive release, so we're releasing component parts in kits to be built and assembled. And as I said, it's all under control of this electronic instruction and assembly method system. So a really exciting time. After probably 2 years of effort, now the team can walk down the yard and see some of these component parts coming together. Begins to feel much more real. If it weren't for COVID, it might be even easier for us to walk down the yard and see these components for real. So unfortunately, much has to be done by video, same as this is today, but there we are. If I go back to my original general arrangement, you'll remember there were more than 4 new technologies in this engine. We're also featuring some of these enabling technologies. Lean burn, that is an UltraFan combustion technology that is capable of meeting the emissions configurations and standards that we expect to be in place within the next decade or for the next decade and beyond. So a lean burn combustion system. Demonstrated incidentally on this, which is a modified Trent 1000 engine in the picture, demonstrated to run on 100% sustainable aviation fuel. So we've conducted that test with a lean burn system. The engine was fine. An important part of our sustainability journey then to show the engine can operate on 100% SAF. Equally, a section of high temperature technology components here. This is a so-called cast bond vane. What do I mean by that? It's an HP nozzle guide vane, but it's actually manufactured in several pieces and fabricated together. Even though it's in single crystal metallurgy, that provides us the ability to put very sophisticated cooling shapes on the inner side of the component during the manufacturing process and use less cooling air for a given temperature in order to increase the efficiency of the engine. Very clever piece of manufacturing technology coupled with clever aerodynamic design process, and you get yourself a very capable metallic HPNGV. That component is complete and ready, and we'll actually go into test on a 97k Trent engine initially, actually, to provide a bit of a mule for us in testing that new technology. And then last but not least on this diagram, here you see a picture of a rig facility that Rolls-Royce is running in Cranfield, or with Cranfield University, on a thing called a cabin blower. So that is a machine that takes drive, either mechanical or potentially electrical, from an engine and uses it to pressurize air for the benefit of the aircraft cabin pressurization system, rather than taking bleed air direct off the engine. Why do that? Well, it's cleaner, for one thing. You avoid the risk of any contamination of air from an engine oil system into the aircraft, but it's actually also more efficient because you can run this machine at its optimum mechanical and the thermodynamic conditions rather than in a conventional engine system, you have to oversize the bleed offtake to cater for the situation where you're providing service air at low engine powers. So this is a clever piece of integrated technology here that allows us to take a fuel burn benefit alongside other environmental benefits by producing an integrated pressurization solution. So there you go, that's a quick whiz through where the UltraFan technologies lie today. As I said at the beginning, the context in which we're delivering this project has changed quite markedly over the last 18 months with the impact of COVID. To be honest, it's felt a lot more difficult now to deliver because of the challenges of COVID, not just disrupting Rolls-Royce, but disrupting the whole of the aviation supply chain. But we're making really big progress. You can see from the images I've just shown you, we've got the component or the individual essential technologies ready to go into an engine. We've got the engine component parts being delivered into the assembly facility, and we've started assembly on the first modules. Perhaps equally importantly, some of the enabling infrastructure is either in place or on the way to allow us to test this big brute of an engine. So the picture at the top here is testbed 80 in Derby, built over the last 2 to 3 years. It's a 15-metre square inlet area, which tells you how much airflow an UltraFan will shift when it's running at max takeoff power. The older beds, which were 14 metres square, were not big enough. So 15 metre square bed, shown here with a Trent XWB, which is the first engine that's run in 80 bed in order to configure the cell. It is the largest and the smartest indoor aerospace testbed in the world. Smartest meaning how much data you can get out of the engine while it's on test in this configuration. Not just raw data, not just things you might think about measuring under normal operating circumstances, but actually now in this bed we're able to test all of the extreme operating conditions that you can test at sea level within 80 bed. Water ingestion, bird ingestion, elements of ice ingestion, fan blade out, you name it, they can all be done, X-ray, they can all be done within this test cell facility. So a fantastic test capability for Rolls-Royce. Testing here with the Trent, but eager, I'm sure, for its first UltraFan to really pull some air through the test cell and put it through its paces. And equally bottom right, an artist's impression here, but this is a 747-400 that Rolls-Royce has quite recently acquired and is in the process of converting as a flying testbed platform for experimental test use. Here's the artist's impression of an UltraFan replacing one of the 524s. If I go way back to the beginning, a reminder of the technology progress that allows you to put that change of bypass ratio into an engine solution now. It's so self-evident when you look at the size of this machine compared to its 524 compatriots. So really exciting set of infrastructures, really exciting time now where this engine comes together for the end of the year, testing next year, really to put proof to all of our claims as to how good the UltraFan might be. This is an artist's impression. I hope before very much longer I'll just replace this with a photograph and it'll be all the more impressive for being real in metal and plastic as the next generation of engine that we're ready to bring to market. So why do we do this? Why is Rolls-Royce doing this? We need to do this. I think it's self-evident from what I said before. Gas turbines are here for a bit longer. Even if we start to see electrical machinery and hydrogen-powered machinery coming into the aviation marketplace, many of those systems will have at their heart a super efficient gas turbine. Certainly at the long-range large aircraft end of the spectrum, a gas turbine is it. And a super efficient gas turbine, which is leading in terms of not only fuel burn, but its emissions conditions and its noise signature, will be even more vital as the world comes back out of the depression of the aviation business than it's been in the past. So, UltraFan, it's clear in my mind, it's a major step in producing the next generation step towards a sustainable aviation platform. And it's clear in my mind, UltraFan Engine 1, Build 1, by the end of this year, early into next year, has to measure up to all our ambition and show that it's capable of these kind of world-leading attributes. Okay, thank you. Well, I hope that's been of interest to you. As I say, I will really look forward to the day we can replace this picture with a photograph and celebrate for real that we have an UltraFan machine ready to burn sustainable fuel.
Great, thanks for that, Andy. That's really good. I look forward to inviting you back. Actually, when you've actually got the thing running and we can see how good it actually is. So that was a very informative lecture. We've got a few questions coming through that I'm going to put to you. They're not going to be any sensible order, I'm afraid, because I can't manage to sort out the order and try and make them particularly. So one from Tim, which is how challenging is the thermal management of the gearbox, given the amount of transmitted power that it's got to deal with?
Yeah, fairly challenging. So the engine has a shared oil system between gearbox and main engine, and fundamentally we have to have some additional cooler capacity. It's roughly a doubling of the cooler capacity a traditional engine might feature. The challenge always in these cases is your corner point situations, isn't it? When you have lots of heat and not so much fuel to dump that heat to. So in the demonstrator engine, some of that heat will be pushed to bypass through air oil heat exchangers effectively. We do have some ideas about how to improve that. Having done the work we have so far for a product, we might have some means of trying to harvest back some of that heat energy. But for the demonstrator, it will use air oil heat exchangers, and it's roughly twice the heat capacity. That's not the end of the world, really. That's manageable. It's a big engine, there's space to put these things.
Okay. Question from Nick here. What thrust class is the UltraFan demo engine, and how does the power gearbox power compare with the Pratt & Whitney GTF? Yeah,
so it's modelled around an A350-800. So if you're familiar with the Trent XWB-84K, that's about a 72 to 75,000 pound thrust engine, and it's sized to that same thrust capability. So 72 to 75,000 pounds. That's about double or a little bit over double the GTF. Yeah, over double the GTF.
Okay, a sort of related question. I mean, I think we saw the issues Boeing had with the 737 MAX and fitting the larger engine, resulting in the wing change, which resulted in all the issues they subsequently had. I think I got the impression from your lecture, this fan or the inlet to the engine is even bigger than the existing engines. Is that going to be a problem with the likes of if you wanted to fit it to future 350 size aircraft, or are the manufacturers going to have to change their design approach to accommodate the larger engines? Yeah,
so is it a problem? It needs change to the nacelle and the pylon integration. So clearly you can't just bolt the engine in place of the existing one. There's some other change required, but it's change below the wing. And I didn't mention it actually, but the UltraFan Demonstrator program, we are in a technology collaboration with Airbus as part of this program. So whilst we're designing the engine, we're collaborating with them on the power plant and the nacelle design. So we will come through this program with an engine that could theoretically fit onto an A350. And you know, that's a big aircraft. It has rudder control capability. It has the integration capability to deal with an engine of this size.
Okay, excellent. Question from Mike. Going back a bit, I think the RB211 and the Trent engines are based on the 3-shaft design. Does the UltraFan gearbox eliminate one of these shafts?
Well, that's a bit of a bone of contention, isn't it? So it's 3 shafts at the front and 2 shafts at the back. That's heretical if I say that actually. So you have an LP spool. The fan system is running at an LP speed. The front of the core is an IP compressor running at an IP compressor speed, 6,000 RPM. There is then an HP compressor running at 12 to 13,000 RPM. So you've got 3 spools there running at different speeds. the subtlety being that the fan and the IP compressor are driven off the same turbine. The IP compressor is driven directly by the turbine, and the fan is driven through the gearbox by the same turbine. So as I say, in effect, you've got 3 compressors and 2 turbines. We would still say it's a 3-shaft engine, wouldn't we? 3 sets of compression running at their own optimal speed.
Okay. Question I was going to ask was, I think the RB211 was seen as a step change in engine design and performance back in its day. Is this an equivalent step change, or is it still more of a incremental growth of that sort of technology?
No, I think this is a step change, and we've classed it as the same. It's a new generation of engine. So we've been very successful in producing a family of Trent engines, which are evolutions of each other, if you like. This is not an evolution of a Trent. This is a revolution. So yes, it is closer to the first 211 than it is to a next generation Trent. Okay. And that's really, to be honest, that's why we have a demonstrator program with 4 engines. You know, it's a major investment, but it's recognition of the fact that the technology level you're trying to deliver here warrants learning those lessons before you launch into a product carrying or passenger carrying product program. Okay.
I think you said hopefully later this year you're going to have it running. How long will the actual physical testing of the engine take? I mean,
well, the EDP program is stretched out over 3 to 4 years, actually, so quite a long period of time. That's 4 engines going through different configurations, you know, so we test, rebuild, test again. So the overall program is 3 to 4 years. The engines themselves, each engine probably accumulate 100 or a couple of 100 hours, not a massive amount. Why is that? Fundamentally because they carry lots of instruments. So these are characterizing the technology rather than operating to a, if you like, a service duty cycle. The instruments tend to be the life limiting feature in the engine because they're relatively delicate. If you put chunky instruments in, you corrupt the very thing you're trying to measure. So you tend to have fairly delicate instruments and therefore they have a short life.
Okay, come out. I guess from what you're saying is then we're unlikely to see this engine in service until early 2030s.
This is where we're in a really funny position, Paul, because of COVID's impact on the marketplace. It's difficult to judge, isn't it, what the airframe manufacturers might do with their product range. So I think a betting man would say end of the decade, yeah.
Okay.
But who knows? You know, the world can change fairly quickly, can't it? As we've all learned.
It can. I mean, yeah. I mean, you asked people 18 months ago, as you suggested at the start, no one would have predicted what's happened in the last 18 months. You know, even probably in the worst case scenarios. So yeah, you're right on that.
And I guess the view has to be, whenever the market re-emerges, you have to be ready. If you're not ready and the market emerges ahead of you, that is a massive missed opportunity. So, you know, that the company has to be ready with the technology, that then we are somewhat beholden to the way the world develops.
Okay. Question on composite blades. So is this the first time composite blades have been used, or are they present in other engines?
GE will tell you they have them in their family of engines. Yeah, so the G90, I think, was the first revenue operation of a composite blade recently. Of course, Rolls-Royce has history in composite blades, not altogether glorious. The early 211 had a dalliance with composite blades, but that was a long time ago and a very different technological solution. But now our competitor engine has composite blades in service today. Okay.
I mean, looking at the picture behind, well, it's not really behind your head, is it? But behind your head, I mean, it looks quite a complex shape of blade you've got there.
Yes, go on. I suppose it's the way of the world these days, isn't it? Very sophisticated modelling tools available now to optimise the aerodynamics. And with a fan blade, probably of all the components in the engine, one of the most heavily constrained. By which I mean it has lots of different requirements it has to meet. Obviously, aerodynamic performance and efficiency. its mechanical robustness to rotating at speed, but also, you know, impact tolerance, ice tolerance. Got to be able to cope with distortion of air coming in from an intake when the aircraft rotates or when it's operating close to the ground and you have a near field effect of the runway underneath the engine. So a whole series of very complex requirements leading you to some pretty sophisticated choices in how you shape the blade. Yeah,
it looks a really nice shape.
They're big. I mean, these blades are very big.
Another question, what's your expectation of the UltraFan engine mass compared to, say, the XWB 84?
So it'll be heavier. I mean, it's higher bypass ratio. It's that's, you know, part of the drive for a composite fan system, of course, is reflecting the fact that with such a big fan system, you carry weight there, and that weight is detrimental. So the overall engine weight is heavier than XWB, but more than offset by the improvement in specific fuel consumption. So when you compare those two things as an aircraft attribute in terms of fuel burned for emission, the SFC improvement of the engine more than compensates for some weight increase on the engine.
Okay, and looks like a final question here. So what are the competition doing? Are they just letting you get on with it, or are they doing something similar?
Well, that's another interesting question, isn't it? I mean, clearly, as one of the previous questions noted, Pratt and Whitney are active in geared turbofan space. So, you know, they've come to the same conclusion about bypass ratio being critically important and therefore wanting to run a bigger and bigger fan at lower speed. GE haven't gone that way. I mean, if we look at our, you know, GE is our sort of most obvious competitor in the big engine market. The GE 9X technology, so that's the engine on the 777X, is a direct drive. It's a bit smaller than the UltraFan in face area, but not, you know, it's still a big engine, direct drive solution.
Yeah.
That relies very heavily on core component technology. It has a limit to what it can do in bypass improvement, and perhaps one of the less obvious aspects of that, if you look at a GE9X, because it has such a big fan system to get bypass ratio, it also has a very big LP turbine, and that impacts how close the engine can fit underneath the wing of the aeroplane. So one of the attractions of a geared turbofan is you don't have that super diameter LP turbine, you go to a smaller diameter, higher speed IP turbine, and you can tuck the engine closer up under the wing, which has performance benefit at an installational level. Okay. So short answer is we don't think GE is active in geared engine technology yet. But you might guess that everybody will end up there because of the benefits of propulsive efficiency.
I guess they're looking for you to pave the way and potentially, I would say, learn from your mistakes. But you know what I mean? Take your technology and move it forward themselves.
Yeah. Maybe.
Okay, I've got one more question here. So, I mean, you might have addressed it, but I don't remember you saying it. So, what is the bypass ratio?
This one's running at about 12:1, but potentially anything up to 15:1. Depends on the installational constraints on the aeroplane.
Excellent. Right, you've got about 10 seconds if anybody else. Oh, hang on, there's another question. From my, what improvement in fuel burn are you shooting for compared with the current technology?
Well, we said 25% better than the first Trent, right? 25% better than the Trent 700, which makes it, I don't know, you know, getting up towards 10% better at an aeroplane level than today's technology engines. That's what the airframers would want, and that's what we're striving for. Okay.
Right, well, I'm going to call it time there. Thank you very much again, Andy, for that. It was very informative.